Dear students, today we are going to see electrostatics. Electrostatics is the branch of physics that deals with the phenomena and property of stationary charges. In this unit we are only going to study about rest charges. What is meant by charge? Charge is a fundamental property of particles. There are two types. One is a positive, another one is a negative. Charges can transfer from one object to another object by friction. Do you know, comb rubbed with the dry hair, it can able to attract piece of paper. Why comb attracts paper? See this video.
Topic: electric charge. How does a plastic comb attract paper? What? You don't believe me? Okay, let us try. Take a plastic comb and bring it close to some pieces of paper. Hey, wait. Don't laugh. We need to do something first. Rub the comb on your dry hair and then bring the comb close to the pieces of paper. See? I was correct. The pieces of paper got attracted to the plastic comb. Do you think it is magic? No. The reason behind this is electric charge. Electric charge is the quantity of electricity held in an object. There are two types of electric charges, positive and negative. However, there are some objects where the positive and negative charges are equal to one another. In such cases, we say that the object is electrically neutral. So, was the plastic comb initially electrically neutral or electrically charged? Initially, the plastic comb was electrically neutral. That means it had an equal number of positive and negative charges. Hence, it did not have the ability to exert a force and attract the pieces of paper. So, after rubbing the plastic comb on our dry hair, why was it able to attract the pieces of paper? I will tell you why. When we rubbed the plastic comb on our dry hair, it gained an electric charge. Once it got electrically charged, it got the ability to exert a force on the pieces of paper and attract them. This charge is called as static electricity. However,
from the above video, we can able to easily understand about charge can be transferred from one object to another by friction. Do you know, glass rod is rubbed with a silk. Glass rod obtain positive charge and silk obtain negative charge. When plastic rod rubbed with the fur, plastic rod obtain negative and fur obtain positive charge. Now see the video, you can able to easily understand.
Of charges were known when charged particles were produced by rubbing due to friction of suitable materials. These facts are demonstrated by simple experiments. A. Suspend a glass rod rubbed with silk. Bring another glass rod rubbed with silk nearer to the suspended rod. It is observed that the suspended rod will swing away, showing repulsion. B. Similarly, suspend a plastic rod rubbed with fur and bring another plastic rod rubbed with fur closer to it. We observe that the rods repel. C. Again, if we suspend a glass rod rubbed with silk and bring a plastic rod rubbed with fur nearer to the glass rod, we observe that the rods attract. From the above, we find that glass rod rubbed with silk acquires something different from that of plastic rubbed with fur. That something is called charge. Unlike charges attract, like charges repel. By convention, the charge on the glass rod when rubbed with silk is positive and the charge on the plastic rod when rubbed with fur is negative. It is due to mechanical friction that the electrons are torn from the atoms.
We can able to see natural charge transformation in our atmosphere. Strong winds move upwards through the clouds and make the water drops present in the clouds to rub against one to another. This rubbing together of water drops produce extremely large electric charges. In that, positive charges deposited upper sides of the clouds and negative charges deposited lower sides of the clouds. When the charge density will be increased means the charges diffuse one to another, it will make lightning. We can able to conclude like charges repel and unlike charges attracts one to another. So in this, the force is acting between the two charges. We can able to calculate that force by using a Coulomb's law. Now we're going to see Coulomb's law. Coulomb's law states that the electrostatic force is directly proportional to the product of the magnitude of the 2 point charges and inversely proportional to the square of the distance between the 2 point charges. Coulomb's law. Consider this is a 1 point charge and this is another point charge. The magnitude of the charge A is Q1 and the magnitude of charge B is Q2 and the distance between them is R. So both are positively charged. So in between that the repulsive force is acting between them. So we have to calculate what is the repulsive force. The force which is directly proportional to product of the magnitude of the 2 point charges. Product of the magnitude of the 2 point charges and inversely proportional to square of the distance between them and inversely proportional to square of the distance between them. We have to remove this proportionality. We have to introduce one constant, that is a K. Q1 Q2 by R square. K is nothing but 1 by 4 pi epsilon naught. The interaction between two charges is determined by Coulomb's law. How does the interaction itself occur? Consider a point charge kept at a point in a space. If another point charge is placed at some distance from the first point charge, it experiences either an attractive force or repulsive force. This is called action at a distance. But how does the second charge know about the existence of the first charge, which is located at some distance away from it? To answer this question, Michael Faraday introduced the concept of field. According to Faraday, every charge in the universe creates an electric field. According to Faraday, every charge in the universe creates an electric field in the surrounding space. And if another charge is brought into its field, it will interact with the electric field at the point and will experience a force. Consider a source of point charge Q. A source of point charge Q is located at a point in a space. Another point charge Q0 is placed some point P. which is at a distance R. This is a point charge present in a space, and another point charge Q0, this is called as the test charge, which is present at a distance R. The electrostatic force experienced by the charge Q0 due to Q is given by Coulomb's law. The force experienced by the test charge, which is given by Coulomb's law. Coulomb's law, F, which is equal to K, the product of the charges, Q, Q0, and inversely proportional to square of the distance between them. It's a R square. So we know that K value, F, it's equal to 1 by 4 pi epsilon naught Q, Q0 by R square. Electric field states that force experienced by a unit point charge and is given by E, it's equal to force experienced by the unit point charge, that is a Q0. E, it's equal to, we already calculated, F, it's equal to K Q Q0 by R square. We have to substitute here K Q Q0 by R square divided by Q0. So we have to cancel Q0 Q0. Finally the E value, E, it's equal to K Q by R square. So here K value, it's equal to 1 by 4 pi epsilon naught Q by R square. We have to apply vector term. E vector, it's equal to 1 by 4 pi epsilon naught Q by R square R cap. This is the electric field present here. Electric field lines. Electric field vector are visualized by the concept of electric field lines. They form a set of continuous lines. Now we are going to see properties of electric field lines. The electric field line starts from positive charge and ends at negative charge. For a positive point charge, the electric field radially outward, and negative point charge, the electric field lines point radially inward. The electric field vector at a point in a space is tangential to the electric field line at that point. The electric field lines are denser in a region A. Electric field has larger magnitude, and less dense in a region B, where the electric field less magnitude. No electric field lines intersect each other. Next topic, electric dipole. Two equal and opposite charges separated by a small distance constitute an electric dipole. In many molecules, the center of positive and negative charges do not coincide. Such molecules behave as permanent dipoles. Example, water, ammonia. Now we are going to see electric field due to an electric dipole. electric field due to electric dipole placed on axial line. Electric field due to an electric dipole placed on axial line. So now we go into see electric dipole. Electric dipole means negative charge and positive charge, both are separated in a very small distance. The center of the dipole is O. From the O, this point, this charge present in a and this charge present in a B. So the distance between the O to B is A, and the distance between the O to A is A. The total distance of the dipole is 2A. This is a minus charge, this is a plus charge, both are separated in a very small distance 2A. We are taking one point C present in a R distance from the center. Now we are going to find what is the electric field. E plus vector, the positive charge producing electric field here acting outward direction, and negative charge producing a electric field direction inward direction. This is a positive charge producing electric field direction, this one is a negative charge producing a electric field direction. So here positive charge producing electric field E plus vector, it's equal to 1 by 4 pi epsilon naught q by r minus a the whole square p cap. So here q by distance between the B to C is nothing but what? From the center to C is r, so we have to take B to C only, so we have to separate from this r minus a. So we are getting the distance between a B to C, r minus a square. Now the electric field due to the negative charge E minus vector, it's equal to 1 by 4 pi epsilon naught q by r plus a the whole square. So distance is what? A to C is from here to there r, we need A to C distance, so we have to add what? Plus a, r plus a the whole square p cap. So in this total electric field is E total vector, it's equal to E plus vector plus E minus vector. E total vector, it's equal to 1 by 4 pi epsilon naught q by r minus a whole square p cap. This is a negatively charged, so this is a negative, minus 1 by 4 pi epsilon naught q by r plus a the whole square p cap. So here we can take common things outside. Q by 4 pi epsilon naught, here 1 by r minus a the whole square minus 1 by r plus a the whole square, the p cap in outside. So E total vector, it's equal to q by 4 pi epsilon naught 1 by r minus a whole square minus 1 by r plus a whole square p cap. So in this we have to simplify q by 4 pi epsilon naught, we have to cross multiply this r plus a the whole square minus r minus a the whole square divided by, this term is look like a a plus b, a minus b term, so we have to write r square minus a square, r square minus a square, and also we have to apply whole square p cap. So we have to simplify q by 4 pi epsilon naught, expand this term a plus b whole square r square plus a square plus 2ra minus of r square plus a square minus 2ra divided by r square minus a square whole square p cap. So we have to write r square plus a square plus 2ra. You have to bring in say negative value, minus r square minus a square plus 2ra divided by r square minus a square the whole square. So we have to cancel, plus r square minus r square plus a square minus a square. So after this we are getting q by 4 pi epsilon naught 4ra divided by r square minus a square the whole square. So here 2ra plus 2ra 4ra. In this term a values are very small, distance between the dipole charges, a values are very small, so we have to neglect this. So we are getting q by 4 pi epsilon naught 4ra by, we can neglect this, so after this r square the whole square gives us r to the power 4. So we have to cancel, it gives r cube. It's equal to q by 4 pi epsilon naught 2 into 2 a by r cube p cap. So we separate this 2 into 2 4a. So because electric dipole value p vector it's equal to, the electric dipole value p vector it's equal to 2a q p cap. So we have to substitute above equation. We are getting E vector it's equal to 1 by 4 pi epsilon naught 2 p vector by r cube.